Welcome back all of you. In the last couple of classes we started discussing about two-dimensional NMR. As you remember, I said for two-dimensional NMR we need two time periods. Double Fourier transformation of two time period gives spectrum in two dimensions, frequency in two dimensions. And then general pulse sequences, we have it consists of four periods: preparation period, evolution period, detection period, mixing period and detection period. Of course I said mixing period is optional. Detection period is always constant. The evolution period is varied as a function of time, systematically, linearly varied. And then based on that, how we have the mixing takes place, how the polarization transfer takes place, how the spins are allowed to evolve in the T1 time period, how the polarization is allowed to mix between the spins among coupled spins or uncoupled spins in the mixing period. That tells you the type of experiment we are planning to do. There are umpteen number of pulse sequences that has been devised so far. Each of these pulse sequence has its own application, and it is designed to extract the specific information in an orchestrated manner. That is what it does. And these experiments can be both homonuclear and heteronuclear. And of course, broadly, I said we can classify two-dimensional NMR experiments into two classes, two types. Instead of classes, I would say two types. One is resolve type experiments, other is correlation type experiment. In the resolve type experiments, the two informations which are inherently present in solution state NMR, like chemical shift and coupling constant, they can be resolved or separated into orthogonal dimensions. That is one thing. In the correlation type experiments, you can correlate information, two types of information. It could be chemical shift among the homonuclear spins, chemical shift among the heteronuclear spins, etc. So, these are all one type of experiments. And I said if you have n time periods, you can have n dimensional NMR spectra, but only thing is the last time period, which is detection period, is always constant, and n minus 1 time periods are systematically varied. And we also discussed about the time required as we go to higher and higher dimensions. I said one dimensional NMR may take few minutes, 2D may take, let us say, 30 to 40 minutes, 3D may take few hours, 4D may take days, and 5D may take weeks. That is what we discussed. And also we discussed about the size of the molecule, how to decide which type of experiment you want, whether it is 1D, 2D or 3D, we can decide about those things. So, finally we came to discuss a special general experiment which is commonly used and first of its kind is COSY, correlated spectroscopy, is a homonuclear experiment. Here it is a two pulse sequence. We have a preparation period, 90-degree pulse, evolution period, another 90-degree pulse, and then detection period. And 90-degree, second 90-degree pulse is also a mixing pulse. And we have started understanding how the COSY spectrum comes, two-dimensional spectra in such a pulse sequence comes. I said this one of the important requirement for the COSY is the spin systems must be J coupled. Here the magnetization transfer or the polarization transfer between two coupled spins takes place through their couplings. Okay, so the coupling is one of the important requirement for this. And we started discussing about how we get the type of spectrum, how type of diagonal peaks and cross peaks. I said when for example particular spin, it has certain evolution frequency, it is processing at certain frequency in the T1 dimension. If it retains the same frequency in the T2 also, we are going to get a diagonal peak. If it gets part of its signal to another spin, part of its polarization to another spin, and then in the T2 dimension it will also come at the frequency of the second spin. It starts processing at the frequency of the second spin. So, it is going to give, that is called cross peak. We took the example of a single spin, we saw it comes in the diagonal. We took the example of two uncoupled spins, and we came to know that two peaks appear on the diagonal and Cauchy spectrum is perfectly symmetric. We took two coupled spins as an example, then we came to know we will get 4 peaks on the diagonal and 4 peaks for a diagonal for A and 4 peaks for X spin, two coupled spins weakly coupled. And also we get two cross peaks at the right side, one at the right side corner, bottom corner of the Cauchy spectrum, one at the top left side corner of the Cauchy spectrum. We get cross peaks. Each of these diagonal peaks and cross peaks are having a square pattern. Then we discussed about the faces of the peaks. I said diagonal peaks, the fine structure is 4 peaks because they are split by another coupled spin. It is a J split doublet in both F1 dimension and F2 dimension. And they all the diagonals are in phase, that is what I said. And cross peaks, again the separation between the cross peaks in the F2 dimension and F1 dimension pertains to J coupling. The interesting thing is the cross peaks are antiphase in character. This is what we discussed and we will continue further from that point today. The signs of the diagonal and the cross peaks in the Cauchy are given like this. Let us look at the spectrum like this. We have two spins coupled. When two spins coupled, we are going to get 4 peaks, a weakly coupled spin system. Let us say this is for A and this is for X, does not matter. We have a chemical sheet of A and chemical sheet of X at the center, and the Cauchy spectrum there is a diagonal, and we get 4 peaks on the diagonal for A and 4 peaks on the diagonal for X, and we get 4 peaks cross peaks at A and X on the top left corner, and also you get 4 cross peaks on the top right corner here. So, this is what you are going to get now. See, this is the pattern you are going to get for a simple two spins which are coupled between themselves. It is a Cauchy spectrum. Now, this is a let us say negative signal and other is a positive signal. So, this is negative and this is positive. Cross peaks are always antiphase in character, whereas look at this one, diagonal peaks, they are always in phase in character. And if you look at take the projection or a cross section, I would say for this one, let us say if you take cross section, both will be in phase doublet, positive in phase, whereas if you take the cross section along this also, it is in phase doublet because again same phase. Whereas on the other hand, you take the cross section for a cross peak, if you take the F2 cross section like this, you are going to see one is positive, other is negative. It is antiphase doublet. Same way if you take the cross section along this one, F1 dimension, again you see one is positive, other is negative, it is antiphase doublet. So, cross peaks are always antiphase in character and diagonal peaks are always in phase in the 2D spectrum. And now the Cauchy pattern of two weakly coupled spin system, if we look at it, now we are going to get 4 peaks. Why are we getting these 4 peaks? What are these 4 peaks for? This is because A appears at its own frequency, it gives rise to diagonal peak. That is what we said, the precessional frequency of A remains unchanged both in the T1 dimension, the T2 dimension. So, it comes same frequency both in the T2 dimension and the T1 dimension, that is a diagonal. And similarly, X appears its own frequency both in T1 and T2 remains same, it gives rise to diagonal peak. Okay. And both A and X spin gives autocorrelation peak. That means this peak among the doublets, for example, this is a doublet, this is a doublet. Between these two doublets, this can correlate to this. There are these two are the doublet peaks. These two are correlating and give rise to cross peak. These are called autocorrelation peaks. Okay, and the frequency of A is modulated at the frequency of X because of its coupled partner. As a consequence, you are going to get the cross peak like this. Similarly, frequency of X is modulated at the frequency of its coupled partner A and gives us the cross peak here. So, these are called the cross peaks, and of course, I wanted to tell you this is the F1 dimension, always the detection dimension is F2. Okay. So, in homonuclear 2D Cauchy, the cross peaks always appear as pairs, they come as pairs. symmetrical with respect to diagonal here. Remember, this is the diagonal, the cross peaks are always appearing as pairs and symmetric is there. There is a perfect symmetry maintained. Okay. Now, how do I use the Cauchy? Simple example, as I said, it identifies the coupled partners. Let us take a simple example to find its utility. I will consider two AX spin systems, two spins which are coupled between themselves. I will consider, for example, forget about this fluorine, I would say instead of fluorine, I will put some other molecule, some other this thing like uncoupled spin. We have two protons here, here two protons here. I will consider only protons, I ignore fluorine is not coupled or decoupled, let us say. These two protons form AX spin system, these two protons form AX spin system. Now, let us look at the Cauchy spectrum for the case of two coupled AX spin systems. Now, each AX coupled spin system gives us to 4 peaks of identical intensities and doublet separation corresponds to JAX, J coupling between A and X, and you get doublet at the chemical shift of A and at the chemical shift of X. Both are observed. This is what we discussed when we discussed about the Pople notation. So I had spin system nomenclature. Now, for two coupled spin system, we get 4 peaks. Now, my question is, which are the two coupled partners? How do you identify that? In the good old days of NMR, what we used to do is irradiate one of them, irradiated by a second radio frequency signal, and then see with a weak RF, RF sufficient enough to see that it is larger than the coupling strength, and see where the spectrum is getting changed. Then we will say this is coupled to this. Okay, this is the simple example. I have taken two coupled spin systems, two such examples. Two mixture. If I have a very big molecule where there are n chemically inequivalent protons, there are several of them are coupled among themselves, then it is a complex spectrum. How many such experiments you want to do? And you have to be extremely careful in doing a selective decoupling experiment to ensure that the neighboring spins are not disturbed. So, it is a very cumbersome experiment. How in such situations the Cauchy is going to help you, I will tell you now. So, let us now take the Cauchy spectrum of this thing to identify what are the coupled partners. One possibility, delta 1 can be coupled to the spin 1 can be coupled to spin 2, possible. That is why equal intensity doublets are there, and 1 and 2 are coupled. There is another possibility, 1 and 3 are coupled and 2 and 4 are coupled. This is another spin system, coupled spin. Third possibility, 1 and 4 are coupled and 2 and 3 are coupled. Now, how do you know which are the two spins which are coupled between themselves to identify two spin systems here? For that, what we are going to do is, we simply run a Cauchy. As I said, Cauchy is going to give the cross peaks between the coupled partners. Now, if 1 and 2 are coupled, these are the diagonal peaks, and if I get the cross peak symmetric with respect to this diagonal, that means I know delta 1 is spin 1 is coupled to spin 2. These are the coupled partners. Then obviously, because of these two are diagonals, again there is a cross peak between these two, then I will say spin 3 is coupled to spin 4. So, I could easily identify the coupled partners just by looking at the cross peaks. So, this is the advantage of identifying the immediate coupled neighbors in any given spin system or any given molecule. Now, this is what I can trace it, go horizontally, vertically up, complete the square, I can complete a square because they are symmetric. Similarly, I can complete the square here and I can say spins 3 and 4 are coupled, spins 1 and 2 are coupled. Now, on the other hand, let us say instead of 1 and 2, 1 and 3 are coupled, that is a possibility. How do you get this spectrum? Now, this is the diagonal peak here and this is the diagonal peak here. I have put different colors to make you understand. Now, if go along this and if I go horizontally along this and see some cross peaks, go vertically up, hit a diagonal, complete the square, then I know you have a symmetric cross peaks. That means this spin and this spin are coupled. So, 1 and 2, 3 are coupled now. That means obviously 2 and 4 are also coupled because this is 2, this is 4. For each of them we get a cross peak like these which are symmetric. So, now I can say 2 and 4 are coupled. Now, you think of the third possibility, If 1 and 4 are coupled, you get a cross peak like this. This is the cross peak. So now I say 1 and 4 are coupled. Okay. On the other hand, if 2 and 3 are coupled, these 4 are diagonals. Now you go horizontally, complete like a square like this. Then I say 2 and 3 are coupled. So you see, depending upon the splitting pattern, depending upon where you get the cross peak, just going through across the from diagonal to a cross peak, go vertically up and see which diagonal you are going to hit. I know this and this are coupled. So identification of the coupled partner is very pretty simple and straightforward in this COSY experiment. You simply go walk across through the diagonal, go from here, go here, and if there is a couple to another one, go like this. You can keep on going in a stepwise manner like this. Okay. So this is what it is. Spin 1 and 3 are coupled, and 1 and 4 are coupled, 2 and 3 are coupled. Now we will take the simple example of a molecule spectrum like this, a realistic spectrum of a molecule ethyl 3 ethoxypropionate in 600 megahertz in solvent CaDCl3, taken from the Leslie Field book. Now let us say I want to identify which are the coupled partners. We have to start from somewhere. I should know which is the peak. We all know in the high field region we get Ca3 protons. There is one possibility, one Ca3 here and one Ca3 here. There are two Ca3s. Now identify which are the coupled partner for this Ca3, this CH3, etc. Now what I will do is I will start with one of them, okay, unless leftmost peak which is isolated. I go from this diagonal, go up, go horizontally, go vertically up and complete a square. Then I know this 6 is coupled to this 7, 7 is Ca3. So that means this is 6, these two are coupled partners, and peaks for these two are identified here and here. On the other hand, now I will start with 2, some diagonal peak here, and go horizontally, go vertically up, it is going to hit this peak. This is Ca3. Now I complete the square. Now it tells me 1 and 2 are the coupled partners. Now what is left over? 2 and 4. This is because it is separated by O in between, the possibility of this couplet to a long range coupling is very, very small or 0. As a consequence, this forms another spin system. Now we have only one diagonal here, we can go with this, start with this, go horizontally, go vertically up, complete the square. Now I know these 2 and 4 are coupled, these 3 and 4 are coupled, these 3 and 4 are coupled. It is very easy to identify even for a bigger molecule like this. Go horizontally, then go vertically. If you hit 2 diagonal peaks, then you find out the symmetric cross peaks. Then you can say these peaks which are giving diagonal, the spins which are giving diagonal peaks are coupled, J coupled. So you take another simple example of a big molecule like this, little bigger. Now we have one identified spin system here, and here everything is a chain. Each proton, like 1 is coupled to 2, 2 is coupled to 3, 3 is coupled to 4, like that. Now how do you identify which is which? Of course, obviously there is one peak which is here, which is Ca3, which comes at the high field. Now I start with one of the diagonal which is also isolated peak here. Go horizontally, hit a cross peak. Go vertically up, hit a diagonal peak, and now complete the square. Now I know this and this are coupled. What are these two? 7 and 8. So this is Ca3 which is coming at a high field. Then I know this must be CH2 which is coming downward because it is attached to C double bond OO group, COO group. Okay. So now you start with the other one. For example, this is another isolated peak which is downfield. I guess this is attached to bromine because it is electronegative atom bromine. So it is coming to the downfield. I start with the diagonal, this diagonal, come horizontally, hit a cross peak, go vertically up, hit another cross peak and complete. So that means this is 1 is coupled to 2. But if you go further, 2, there is another cross peak, you can complete a square like this. That means this has to be 3. 2 is coupled to 3. Next one is immediate neighbor. Then 3 should be coupled to something else. 3 must be coupled to 4 here. See, 3 must be coupled to 4 here, and then you can complete, you can say 4 is coupled to 5. I didn't write here 3 is coupled to 4 like this. So like this, systematically you can go walk across the cross peak and diagonal peaks and identify which are the immediate coupled neighbors for a particular spin, for a particular group, chemically inequivalent group. So this is how COSY is a very, very useful experiment. We can discuss lots and lots about this thing. Varieties of ways Cauchy experiments have been there, designed. There are several variants. We will not be able to touch upon everything. Maybe one or two we will discuss. But there are certain limitations for the Cauchy experiment. It is a very old experiment which was first utilized by everybody. Most of the people were using Cauchy experiment for identifying coupled partners. One is J coupling is an important thing. Polarization transfer takes place between coupled spins. So coupling is important and depends upon the coupling strength. Okay, it can go to 2 bond, 3 bond also, extend to 3 bond if there is a strong coupling. Coupling strength is larger. And all the 2D peaks have fine structure. When there are multiple resonance peaks, then it can give rise to some. It gives us a diagonal peak and cross peak. There could be overlap also. And as I said, cross peaks are antiphase in character. We have positive negative intensities, where diagonal peaks are both in phase, both are positive peaks. And if there are broader signal, positive negative signal get cancel out, and you may not get the multiplicity pattern at all in the Cauchy, especially when you are looking at the cross peaks. When you look at the cross peaks, because of the antiphase character, if there are broad, if the peaks are very broad, positive and negative peaks get nullified. Of course, diagonals are in phase. Huge diagonal peaks will be there many times if there is a strong peak. Near the diagonal peak, if there are cross peaks, it is very difficult to identify because you get tiles. We call as tiles on F1 dimension, F2 dimension. At the strong peak which is there on the diagonal, that will obscure the cross peaks coming close to diagonal. So these are all some of the limitations of the Cauchy. The cross peaks, strong diagonal peaks will mask the cross peak close to it because of the tiles that are coming to the strong peak. So certain line shapes of an NMR spectrum, especially not only for Cauchy, all the 2D spectra, there are certain line shapes, which is well known. These are the terminologies that we utilize. This is called a spectrum of this pattern, which is like like a star. This is called pure absorption line shape. Absorption both in the T1 dimension and T2 dimension, it is called double absorption, double absorptive peak. And this is a pure dispersive peak. You see, antiphase character will be there. It is not like dispersion. Absorption is like this, dispersion is like this. We have been discussing this long ago. And then phase twisted line shape like this. These are the things which you see. This is you see like this in the contour, whereas these are these are the stack plot. These are the contours. You have different shapes like this. These are the common line shapes you come across in many or all the 2D spectra. So how do you represent the 2D then? You can represent the 2D spectrum when you want to record the spectrum. It is represented in two modes. One is called phase sensitive mode, other is called the magnitude mode. In magnitude mode, phase information is lost. You know how to get the magnitude? Sum of the real square plus imaginary squares and then take the square root of that. Magnitude mode, there is no phase information at all. It produces line shape in which the absorptive and dispersive parts are mixed up. So you will not get high resolution. It is not suitable to get high resolution. For representing a high resolution spectrum, I tell you, as we go ahead, we must get double absorptive peak. Then resolution is much better, always better. So this type of magnitude mode representation of the spectrum is not suitable for high resolution. So, and also phase sensitive data, line shapes in absorption dispersion mode are separated out, whereas in the magnitude mode it is not possible. So that is the reason why absorption mode is preferred, and in the case of Cauchy, because of the magnitude mode representation should be done always, it is not very well preferred. But of course, many ways people have overcome this method, everything, number of variants are there. So this is how the magnitude Cauchy looks like that. If they take the spectrum of any, let us say again two coupled spin system, we AAX spin, we have diagonal peaks and cross peaks here, and you can see the pattern like this. Cross peak and diagonal peaks have mixed phase. They are absorption dispersive line shape, both are there. So dispersive component gives us the long star shaped ridges like this in both dimensions. You see, here in this dimension and this dimension you get a star shaped ridges. So this is what the problem of the magnitude Cauchy, magnitude way of representation. Then you have peaks very close here in the high resolution. you will not be able to identify them. These are the problems with the magnitude representation of the Cauchy. In another important thing what I want to tell you is, when you take any 2D spectrum, when you do the double Fourier transformation, in any Fourier transformation we discuss, when we discuss about the Fourier series and Fourier transformation, take a simple cosine wave. We said you will have a real part and imaginary part, we saw that. Similarly, sine, if you take the sine wave, we saw real part and imaginary part. So, in both f1 and f2 dimensions, we have real part and imaginary parts in each of them. So, that means both of dimension, if you consider, we have both real parts and imaginary. There are 4 possibilities: real, 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 imaginary, imaginary, real, and imaginary, imaginary. So, there will be 4 different quadrants you can think of, the way we can represent a signal. For example, this is imaginary in one dimension and real in the other dimension. In this case, both are imaginary, imaginary. See, in this case is real here, imaginary here, and this is both are real, real, and here real in this direction and imaginary in this direction. So, only the important thing is real, real quadrant. This is where you have to represent the spectrum in the 2D spectrum. This is how you have to represent the cross peak. This contains double absorption mode and this provides highest resolution. See, if you plot like this, you will not get better resolution. Whereas you see, if you look at this, you can see the difference between this and this, it gives better resolution. So, the best representation of the 2D spectrum is always in a double absorptive mode, you get better resolution. So, double absorption mode is always preferred for highest resolution. Please remember, if you record a 2D spectrum, double absorption mode is highest preferred because of highest resolution. Magnitude mode is not at all preferred because it gives ridges and mixed faces, everything. It does not give, it is not suitable for high resolution. So, with this having said, we can go to other types of 2D experiments. Before that, we look at some of the variants of the Cauchy sequence very quickly. This is a simple 2-pulse sequence, but this has been modified over the years by several stalwarts in the NMR spectroscopy to derive information, to overcome the problems and to enhance the resolution, sensitivity, etc. So, as a consequence, several variants have been developed. We will concentrate only on 1 or 2. Okay. One is important, is called DQF Cauchy. What is DQF? Double quantum filtered Cauchy. For example, what is double quantum, what is single quantum? Maybe after 2D I will take multiple quantum, there we will discuss. Double quantum is, I told you also, 2 quantum. This is 0 to 1, let us say the single quantum, and 0 to 2 if you go, the spins undergo flipping from, let us say, it is double quantum of energy, let us say alpha alpha goes to beta beta, it is double quantum. So, what we can do is we can select a pathway in the Cauchy 2-pulse sequence here, and in between there is a delay. As I told you, remember when we were talking about the coherent pathways selection, first pulse always creates +1 -1 coherence, and any second pulse always creates multiple quantum coherences. So, it is going to create higher quantum coherence, for example, p is equal to -2 and +2 and -2 like this. Now, whatever the pathway you choose, finally we should come to -1, p is equal to -1. This is what generally in all the spectrometers it is detected. We have to choose finally p is equal to -1 pathway. But what we can do is, this can be done by phase cycling or also by gradients, both we discussed. So, what we do is, we can, there is a double quantum filtered, means after this +1 -1 is created, the second pulse will create higher quantum. Let us say there is a second quantum here, from +2 I will come to -1. From +2 to -1 there is a way we can select the coherence transfer pathway by both by gradients and phase cycling, we discussed that. Now, when you are going for double quantum, what will happen? It is a filter, you go from here, you come here directly. So, advantage is large single quantum let us say peaks which are singlets or solvent peaks, reference peaks which are all singlets, you will completely suppress it. So, double quantum filtering has a lot of advantages, and now this sequence is similar to Cauchy. Second integrity pulse generate multiple quantum coherence, I told you, which is not detected by the receiver. Even in the Cauchy, what we discussed, 2 pulse sequence, 90 tau 90, 90 T1 90 sequence. Second pulse always creates multiple quantum coherence, but our receivers will not see that, it will not detect. So, in DQF Cauchy, what we do is, as I showed you, we go to +2, let us say double quantum, select the coherent transfer pathway from DQ, bring it to -1. So, what we do is, we convert double quantum coherence to single quantum coherence by third pulse, and then we detect that. Select the coherence, and the third pulse we are going to detect that. So, the selection of DQC is by phase cycling or gradient. You select a particular pathway between last 2 pulses, and then you can do it, do the phase cycle like this. This is exactly, we took one of the example for delta P is equal to -3 from +2 to -1. Let us, don't worry about the pulses here and here. I am just showing you this we discussed. From +2 to -1, here delta P is equal to -3, P1 is equal to 2 and P2 is equal to -1. And we discussed both from gradients, using gradients, and also by using phase cycling, how we can select this particular coherence transfer pathway. We discussed this, and these are the phases where we worked out for the when the pulse phase is like this, transmitter phase, and this is what we are arrived at the receiver phase, and this is the equivalent phase. We discussed everything. I am just giving you this thing. There are ways you can choose different pathways. It need not be one. There may be several ways of choosing the particular pathway. Accordingly, you have to choose the phase cycling. Okay. So, the receiver phase goes in this opposite phase in the pathway that I have chosen like this for this phase cycling. Now, the DQF Cauchy experiment with coherence transfer phase selection, we can also use gradients. How do you do with gradients? We discussed, even worked out this one also again. Here the gradient ratio has to be 1:2, in which case it will select the double quantum pathway. You please go back to my pulse field gradients when we discussed, we use the gradient ratio 1:2, so to select this double quantum pathway. So, both way we can do gradient pulses, and we can use phase cycling. But in addition to that, we use a phase, in addition to that, spin-echo sequence also. This is to get phase sensitive representation, that is possible. Okay, more details let us not discuss, but this is the idea. We already discussed how to select the phases, how to select the coherence transfer pathway using gradients. So, in any way, in the phase cycle DQF Cauchy, both coherence pathway +2 to -1 and -2 to -1 are retained, which is called P peak and N peak, both are retained. The gradient experiment detects only one coherence, +2 to -1. Only one of them is retained. That means gradient version is poorer by 2-fold, because you have double the signal here, here you have only half the signal. So, gradient version is poorer in sensitivity by 50%. That is the important thing. You remember, phase cycle version is having better sensitivity, because you can get both P and N type peaks, both can be chosen, both are retained there. That is the advantage of using phase cycling even in the DQF Cauchy here. So, both again diagonal and cross peaks here possess antiphase absorption mode Shell shape, and they are not affected by double quantum filtration at all. What did we do? We use the double quantum filtering by choosing the pathway from +2 to -1. Okay. And then nevertheless, we have antiphase character for both diagonal and cross peak. They are not unaffected BQ. As a consequence, what happens? If there is a tailing near the diagonal peaks, as we observed in the Cauchy, it is not there, the tailing will be removed. So, it is going to give you a better quality spectrum. The biggest advantage of DQF Cauchy is it gives you a better quality spectrum compared to Cauchy spectrum. Another advantage is, if you have singlets coming because of uncoupled protons or solvent peak, for example CHCl3, only one peak will be there. A reference TMS, only one peak is there. All of them are removed. All peaks, singlets coming from either of them, either any of these people, any of these coupled part protons, solvent peak or reference peak, everything can be removed by double quantum filter. So that is the reason why DKF Cauchy is widely used because of removal of dispersive components of the diagonal peaks. Very important. Please remember, I will show you a simple DKF Cauchy spectrum here. Look at it. These are cross peaks. These are diagonal peaks. The different signs here, which is given in orange color, and the close or otherwise say close contours and open contours shown here, they have opposite phase. One is positive, other is negative. Signs are opposite. Okay. So both diagonal and cross peaks here you have antiphase character. Both the dimension. In this dimension also antiphase, in this dimension also they are antiphase. Not only the cross peak, even the diagonal also. Both are antiphase. So they are double absorptive. So diagonal peaks will not mask the peaks nearby. So the coupling can be measured due to better resolution. See, the peaks which are coming very close to this thing, or even to diagonally here or here, we can very precisely measure because there is no tailing and resolution is much better. So look at this spectrum. A very simple molecule, it is a pentapeptide. Look at this is the Cauchy spectrum, conventional 90T1, 90T2 sequence. Look at the type of spectrum here. These are all the diagonal peaks. See, these are all the cross peaks. See, near the diagonal it is so clumsy, there are peaks you will not be able to identify. On the other hand, look at this, the DKF Cauchy, the same molecule. Look at the clarity of the peaks, both in the diagonal and in the cross peak. That is why never do the Cauchy experiment if you want to get a better resolution, and so you always use DKF Cauchy experiment. It is only slight modification of the Cauchy, but gives you better resolution and better clarity of the peaks, with especially close to the diagonal. So with this DKF Cauchy, I am going to stop because time is coming up. What we will do is we will discuss another simple one or two variants of the Cauchy in the next class. So here we discussed today about the Cauchy, the types of the peaks we are going to get, both phases of the diagonal peaks and cross peaks. In conventional 90T1, 90T2 Cauchy, diagonal peaks are in phase, cross peaks are antiphase in character, and it gives us a large tiles near the after diagonal peak, and because of that the peaks near the diagonal gets masked, and it is always have to be mentioned in the represented in the magnitude mode, and is not good for high resolution. As a consequence, the modified version we discussed is a double quantum filter Cauchy, where you use a double quantum filter. Because of the third pulse, what you are going to do, the second pulse creates a multiple quantum, and you filter it to select a particular pathway from +2 to -1 or whatever the pathway using phase cycling or gradients, and the third pulse convert the double quantum into the single quantum detection and detect it. And we observed here both diagonal peaks and cross peaks are antiphase in character, and it can be represented in double absorptive mode. It gives better resolution and better clarity, especially for the peaks close to the diagonal. So that is why DKF Cauchy is always advantageous and preferred over the conventional 90T or 90T2 Cauchy experiment. Okay, with this I am going to stop now. We will come back and continue further in the next class. Thank you.